Hello, so I guess we can get started with the second half of the change point detection tutorial. So it's my great pleasure to be able to present to you the second half, which is entitled Introduction to Supervised Change Point Detection. So I'm a machine learning researcher, and I've been trying to develop algorithms that make it easy for people to use supervised machine learning to choose what is the right change point model for their data. So I'm going to be explaining how that works in the R programming language. So if you want to follow along, what I suggest to do is go to the repository on GitHub. You have github.com/tdhawk/change-tutorial. And you have a few links down here under Toby, that's me. And so the first thing I would recommend you click on look at the rendered RMD here. And so that's going to give you a web page like this, where you have some R code blocks and you have some figures that we're going to discuss. And then the second link that we have here is a link to an R Cloud notebook. So I heard about this last year at Simon Urbanek's really amazing keynote at useR 2016. And hopefully we're going to have an internet connection in this room so people can follow along and do the exercises on R Cloud. So when you click on that link there, you should get a web page that looks something like this. This is the R Cloud interface. And it should say something like this at the top, TDHawk exercises test read only. And so if you want to edit the exercises and execute the code, you're going to have to fork it by clicking on this fork link. And so hopefully this will fork a copy of this R Cloud notebook to Rebecca's GitHub, because I'm using Rebecca's computer. Yeah, the other option to follow along is that we have some scripts in the repository here. So I have a link to the source file, supervises exercises.r, and you have also the source code of the RMD, which you could open in RStudio, but that's not really recommended because there may be different version problems. So it's really probably a more sure bet to follow along on the R Cloud notebook. And so normally, once you've clicked the fork button on the R Cloud notebook, you should see your GitHub username, and then exercises test, and you should see a bunch of code in the middle here. And so the idea is we're going to be editing this code and then seeing what the results look like. And so what you can do just to start off is just click the play button, and that's going to just execute the code once for the whole R Cloud notebook, and then we're going to go in and we're going to edit specific parts later and see what that changes. But it's a good idea to do this once at first, so then we don't have to wait for it later. And yeah, so the subject of my talk is going to be Introduction to Supervised Change Point Detection. And so I've divided my talk into kind of two parts. And the first part is called What is the difference between unsupervised and supervised change point detection? So Rebecca gave a very excellent introduction to unsupervised change point detection. And so in this first part of my talk, I'm going to explain what is the difference when we're in the supervised machine learning setting. And then in the second part of my talk, I'm going to explain about a typical supervised change point analysis using the penalty learning package that I wrote and then recently put on CRAN. So I'm going to go through all of the steps that you would have to do to perform a typical supervised change point analysis. And the data set that I'm going to use throughout this tutorial is going to be the neuroblastoma data set. So let's go down to this first section. Well, actually, before I get into the details of the neuroblastoma dataset, first I'd like to just emphasize, so what is the difference between unsupervised and supervised change point detection? Well, there's really two key features of a dataset that make it suitable for a supervised change point analysis. The first thing is that there needs to be several different data sequences with similar signal noise patterns. And so each one of these data sequences are going to be treated as a separate change point detection problem. And the second feature is that some data sequences must have some labels in specific data sequences and specific regions that indicate where the model should predict presence or absence of change points. And so these labels are basically going to be used to learn a model which is consistent and is able to predict an accurate number of change points for each one of these data sequences. So yeah, the neuroblastoma data set is going to be the data set I'm going to be discussing for the next 90 minutes. And so this is a data set that we put on CRAN in the neuroblastoma package as a part of my PhD work at the Institute Curie. So when you load this into R and you look at the structure of the neuroblastoma object, you see it's a list of 2 data frames. The first is the profiles data frame, which is a list of about 400, with about 4 million rows and 4 variables. And then, and so these are the raw data that we're going to be segmenting or doing change point detection on. And then, crucially, you have this second data frame, which is annotations. And these are the labels that indicate the presence and absence of change points in specific regions in this data set. So another way to look at that is by just looking at the first 10 rows of each of the 2 data tables. And so for this profiles data table, what you see is you have these profile D and chromosome columns, which are used as identifiers for indicating the separate change point problems. And then you have position, which is going to be the x-axis of the change point detection problem, and log ratio, which is going to be the y-axis in the change point detection problem plot. So, so to give you some biological context, so these data come from patients who were having neuroblastoma. It's a rare form of childhood cancer. And so basically what they do is they do these kind of experiments where they're measuring for every chromosome and for every patient and for every position in the genome, what is this log ratio measurement? It's going to be a noisy measurement of the number of copies of every chromosome. So by analyzing these data, we're going to be able to figure out if there are any chromosomal copy number abnormalities. And so we're going to be able to see that in a figure in a minute. And so crucially, these data also contain these annotations, which are indicating for a specific patient or profile D and a specific chromosome in that person's profile, and then for a specific region in that genome, here indicated with min and max, is that region of should that region have a change point or not? And so that's what we see in the annotation column of these data. The normal rows are the ones where we know that there should be no change point predicted, and the breakpoint rows are the ones where we know that there should be at least one change point predicted. So this is a really crucial part of the data set that make it appropriate for doing a supervised change point analysis. We know where the change points should be in a subset of the data. So to make this a little bit more concrete, let's go down to the first figure. Here I've just got some code which is selecting a few of these profiles, and it's going to be plotting them using ggplot2. So I'm going to use just a geom point to plot 6 of these profiles I'm mapping position to the x-axis, log ratio to the y-axis, and then I'm using a facet grid, which means I'm going to be drawing a different panel for every profile and for every chromosome. And so let's see what that looks like. So that's this first figure where you can see, like I said, oops. So here we have, like I said, one panel for every different chromosome, which is going from left to right here, chromosome 1, chromosome 2, chromosome 3, etc. And then you have one panel going from top to bottom for each one of these different profile IDs. And so actually these are different patients who came into the Institute Curie for cancer treatment. So you can see every one of these rows corresponds to what is the measure of their copy number for their genome. And then also on the, so like I said, we map the position on the chromosome to X variable, and then we map this log ratio the y-axis. So basically, the task is for every one of these boxes, try to find where the change points are. So you can see very clearly, like for example, in chromosome 1, you have a change point in the first half. In chromosome 2, you have a few change points here for this particular patient, whereas with other patients, you see that it's more of a flat profile. So the goal is to try to detect for every profile, for every chromosome, where are the change points, if there are any. And you can see already, we're only looking at a very small subset of these data, actually. So here, it's only 6 rows, but in fact, in the neuroblastoma data set, we have a database of 575 of these different profiles. So we're clearly in this big data setting. So there's clearly a lot more data than we could ever possibly analyze by hand. So just one thing about these data, which is really kind of like the motivating thing for doing the analysis for me, is that when you, the reason why it's important to detect the change points in these profiles is because these are really used as a clinical indicator. So the doctors actually are looking for breakpoints in these profiles, and they use this to kind of predict if the patient is going to have a relapse or not. So you can see that on the right side of these figures here. So the top 3 profiles are okay because we know that these patients recovered after their initial treatment. They didn't need to come back to the hospital for treatment. And the bottom 3 profiles, sorry about that. The bottom 3 profiles are called relapse because actually we know these 3 patients actually did have to come back to the clinic for additional treatment because they had an advanced form of cancer. So the way that the doctors do this classification is basically they're going through these data and they're looking for change points. And so when they see a profile like this, where you see a lot of change points in individual chromosomes, like here, 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 or here, right? They're going to classify this patient as probably one of the relapse patients. So in contrast, one of these OK patients is pretty much constant within each chromosome, so they're going to be able to target their treatments based on where they see these change points. So it's really important for the doctors to get an accurate change point model so that they can accurately give the patients a treatment in the clinic. So, so yeah, that's kind of like what the profile, the noisy data look like. So this is kind of, we're still in the context of unsupervised change point detection. This is what Rebecca was talking about in her part of the tutorial. So to make this a supervised change point detection problem, we needed to know for a specific set of profiles, where should there be change points? And so that's what we see in the next figure. So here I'm, in the next code block, what I'm doing is I'm adding a geom to the previous ggplot. Here I'm using a geom tolerect, which is a new geom that we've defined in the penalty learning package. And it's practical for rendering these labels because basically they're labels which are specified only with respect to the x-axis. The y-axis is always from the top to the bottom of each plot. And so what you see in this plot is that I've superimposed these labels. So the purple labels are breakpoint labels, which means that there should be exactly, or at least one change point predicted somewhere in this purple region. So actually what happened is these doctors, they go through and they look at these plots and they say, okay, well, clearly we don't know exactly where it is, but we know that there is definitely a significant breakpoint somewhere in here. So so if you give us if you learn a model, it better at least have one change point in that region. And so similarly, they give us also a set of these negative or normal regions that say, okay, well, we don't care exactly actually, so we've looked at these data and we can clearly see that there's no significant change in this region. So whatever model you give us, there better not be any changes, at least in these orange regions. So you can also see that there's a lot of data sets that don't have any changes at all, that don't have any labels at all. Like for example, all of sorry about that, all of chromosome 5, 6, 7, 8, 9, and 10, they don't have any labels at all. So these are data sequences that we're not sure, and the idea is that what we want to do is we want to learn from the limited labels that we have on the other chromosomes with these colored rectangles, and we want to be able to have a model that's able to predict consistent breakpoints for all of the data that we don't have enough time to label manually by hand. So is that okay for everybody, or are there any questions about the supervised change point setting? Yeah.
So if I understand you correctly, you're looking at some chromosomes, you're labeling, and you're using that information to detect it on other chromosomes.
Yeah, that's right. So the question was, you're looking at some chromosomes, you're labeling those, and then you're trying to use that information to detect changes on the other ones. And that's exactly right. So it's the classical kind of supervised learning context where we have a lot of data, but only a few labels. And we want to be able to learn from those labels to do an automatic classification of all of the rest of the data. So yeah, it's clear from these plots that these data satisfy the two criteria for a supervised analysis. Again, there are several different data sequences with similar signal noise patterns, and they're treated as separate change point detection problems. And some data sequences have labels which indicate specific regions where the model should predict presence or absence of change points. So you can apply this kind of supervised change point analysis in any data set that satisfies these two criteria. So now I'm going to go explain how you can use these labels to compute the error of an unsupervised change point detection model. So in the next code block, what I'm doing is I'm defining unsupervised penalty, the 6-0 penalty. So this is the Schwartz information criterion that's defined in the change point package. And what I'm doing is I'm just going to fit this change point, just a change in mean, to all of these profiles using this SIG penalty, and we're going to see what that looks like. So this is just saving the change points in a format that's appropriate for ggplots. And then, yeah, again, so we have to slightly reformat the data here in order to have it in this format where, because we're going to be plugging into this function called penalty learning label error. So this is going to compute the error of the change point predictions with respect to our labels. And to do that, you have to have a data frame that looks like this, where you have columns for IDs for the separate change point detection problems, here profile ID and chromosome. And then you have a column that has the predicted change point locations. That's the change column here. And so once you do that, you can plug into this label error function, and that's what we're doing here. So basically, you just have to give it the description of the different models that you computed, the description of the labels, and then the description of the change point locations. Each one of these is a tidy data frame. And what you get is you get a list of two data tables. The list has two named elements. The first one, model errors, is a row for every sequence and model, and it's the total number of incorrect labels. And then label errors, this is one row per sequence model label combination, and it's going to have the false positive, false negative status for each label and each predicted model. So we're going to use this in the next plot to visualize the false negative and false positive rates. So to do that, in the next plot, I'm using a ggplot with geom vline to visualize the change points here, and then a geom tolerect again to visualize the label errors. And here I'm using line type equals status, so the border of the rectangles will indicate whether or not there's an error. So this is what the unsupervised change point model looks like. You have a few change points predicted using these vertical green lines, and then you have so you see that there's a few of these purple regions where we know there should be a change point, but there's no green vertical lines, there's no change points predicted. So that's why we draw this black dotted border, which means it's a false negative. So that means that we should have predicted a change point. We know that the doctors told us there should be one, but the model's not predicting one. So we can quantify the error rate using these labels. We can say that there's 4 incorrect labels, and so this is the basic idea of the supervised learning. What we're going to try to do is we're going to be trying to find a change point model or a penalty function that is going to give us a minimal number of incorrect labels in this very specific sense. And so, yeah, so here we see false negatives. We could also have false positives depending on the model, right? We're not seeing that, but that would be if we predict a change point in one of these orange regions where we know there should be no changes. And so the correct labels are the labels with no border, so you see that these are all correct because they don't have any changes. And these purple ones here are correct because they do have changes predicted. So a quick remark about this particular result. So what we're observing is that the big penalty produces too few changes, resulting in false negatives. So this is specific to this neuroblastoma data set. However, in general, you can expect that using an unsupervised penalty function in whatever data you're analyzing, it will have some kind of change point detected errors, change point detection errors that are visually obvious. And so this is the main motivation of doing the supervised analysis. If the default penalties are not working for you, you can always add labels and try to learn a penalty function that will be consistent. And so now we can go to the first exercise. And so basically what the exercise is we're going to try to experiment with different penalty values and different data sets to see if we can find another unsupervised penalty which has a lower number of incorrect labels for these data. So I'll invite you to go to the R Cloud and see if this is going to work. I think I already read it over here. So, all right, so in this in this second code block here, I say exercise 1, and so the exercise is to change the IDs here, which are controlling the different rows, the different data sets we're displaying here. And then change the pen name here, and there's several different default penalties that Rebecca explained in the last session. And so, like for example, here I changed the IDs to these values, and now we're using the MBIC with a modified Bayesian information criterion, and you can see it gives you can see what the results look like down here. So for the MBIC in these other data sets, we see it's also having some false negatives here again, 3 purple regions where it should be predicting a change point, but it's not. And so we can see what happens when we use another penalty. So I invite you to experiment with different values on your own computer too. Like for example, Hannah and Queen, right? That's another option, right? Hopefully this works. So it turns out that this unsupervised penalty is doing a little bit better, right? So it looks like it's only got 2 incorrect labels instead of 3. And we could try to change the penalty and try all of the different unsupervised penalties that Rebecca proposes. But this is the main motivation of the supervised analysis. Rather than trying all of the different values of an unsupervised method yourself, what you can do is you can just plug into the algorithms that we propose, and it's going to just directly learn a penalty that is consistent with the labels. So you don't have to do the guesswork yourself. It's the machine learning algorithm that's going to figure it out for you. Okay, and so yeah, the second part here is going to be about just a little quick aside to explain like how do you actually create these labels in practice? So, like I said, for this particular data set, what we have is we have these labels that say, yes, there's definitely at least one change point in these purple regions, and no, there's definitely not changes in these orange regions. But like in practice, how do you do this for your data sets? So in general, I would recommend using some kind of graphical user interface for whatever you guys are using for your data. I mean, it's like what I did is I wrote some GUIs that are specifically for these kind of copy number data, where you can actually draw on the plots and these rectangles appear, and the people can really just interactively just add labels wherever they see them, you know, as they're browsing through the data sets. So I have a link to a couple of software systems that I created for this purpose. But I guess so for different kinds of data, you're going to have different kind of labeling, data visualization and labeling issues. So perhaps you're going to have to implement your own. But even if you don't have GUI software, I just wanted to show that you could do this yourself in R just by you know, creating a CSV file, or even just like typing the numbers in our code, right? So for example, if we take this particular sequence in the neuroblastoma data set, you know, we can say, okay, well, it looks like there seems to be a change point somewhere between 70 and 80. And then, you know, we can type the numbers down here. So here I actually typed between 70 and 90 and between 20 and 60. So for a 1 change and for a normal label. And then, I mean, you just have some labels for your data set. So yeah, that was just to give you some idea of where these labels are actually coming from. So typically, in my experience, when you work with different domain experts, they have some idea of like what is a significant change and what is a not significant change. So basically, you just have to ask them to write that down in some specific locations where they are sure, and then you can use that for your analysis. So now I'm going to go to the second part of the talk, which is a typical supervised change point analysis. And so now I'm going to go through all of the steps that that you can do using our code to do this supervised change point analysis, learn a penalty function with optimal change point detection accuracy. So I've divided it into several steps. The first thing that you need to do is you need to compute a sequence of change point models with increasing complexity. Second thing you need to do is compute this label error function, which is like what we saw in the last section, was the number of incorrect labels for every one of these change point models. Then we need to compute this model selection function, which I'm going to explain. It's mapping between penalty values and models. And then we compute the outputs and the inputs for the machine learning problem. So the outputs are going to be a target interval of penalty values that results in optimal number of change point detection errors. And then the inputs are going to be some like simple features of each one of these data sequences. So we have, once you do that, you can plug into any number of learning algorithms. It results in an interval regression problem, so you can plug into the survival servreg function, or we have a L1 regularized squared hinge loss solver called interval regression CV that I'm going to discuss as well. And then after you do that, you have some learned model. You might want to evaluate what is the prediction accuracy of that model. So I'm going to discuss briefly some cross-validation experiments that you can do to quantify the prediction accuracy once you've learned one of these models. So for further details, I refer you to our ICML 13 paper where we describe this in mathematical detail. And so I'm going to try to skip most of the math and focus on the different coding steps that you would have to do this kind of analysis. So the first step is to compute a sequence of change point models of increasing complexity. So to explain this step, I'm going to zoom into just one of these data sequences instead of showing that whole big matrix of all of those different data sequences that we looked at before. So in this ggplot, we're just showing one of these data sequences where I gave that negative and positive label here. So again, the normal orange label means that there should be no change points predicted in this region. And here, this red one change label means that there should be exactly one change predicted in this region, not 0 changes and not 2 changes. So it's different from that purple region that we saw before. And so then what we do is we're going to compute a sequence of maximum likelihood Gaussian segmentation models. So this corresponds to using the CPT mean function that Rebecca was discussing. And the idea is that some of these models are going to be consistent with the labels, and some of them are not going to be. And so we're going to use that information to learn which ones are how to predict a penalty that is consistent. So to compute this sequence of models, I'm going to introduce the segmentor3 is back segmentor function. And so this is not my work, but I'm using this a lot. So this is our package from my colleagues in France. And there's some references at the end of the section. But what it does is it's going to compute a sequence of maximum likelihood segmentations from 1 to Kmax, and where Kmax is a parameter that you can specify. So Rebecca was explaining that there's this crops method where you can specify a range of penalty parameters, like from 5 to 500 or something. So this is kind of an equivalent, but instead of specifying the penalty, you're specifying actually the number of segments or the number of changes. And so here, what it looks like in our code is that you specify the number of segments, and then you call the function with a particular data set. So here, this is the vector of numeric noisy data. And then model equals 2 means to use the Gaussian likelihood, and then we use Kmax equals max segments to indicate that we want to go up to 7 segments or 6 change points. The output that we get from the segmentor function looks like this. It's a S4 class with a bunch of different slots. The thing that we're going to be using is the matrix of breakpoints. So this is completely equivalent to what Rebecca was showing when you use the crops method. You have, for every model from 1 to 7 segments, you have what are the last positions of each one of those segments. So here, this is the first change. This is the change point in the 2-segment model. So these are the 2 change points in the 3-segment model, etc. You notice the diagonal is always 76 here because there's 76 data points in this particular data set. And so some other things you get from the segmentor function is you get the segment mean parameters. It's also a matrix here, but you don't see it quite as clearly in this output. And you also get the likelihood, which we're going to be using for computing the model selection functions. So next, what we have to do to use these supervised learning functions, we have to convert this kind of S4 class object to a tidy data format, and this is what we're doing in this next code block. Essentially, basically, we just have to extract the relevant information from the breaks slot of the S4 object, and then convert it into something that makes a tidy data frame that makes sense for the functions that we're going to use later. So, for example, here we're making a data table with 1 row for every segment, so you can see there's a start and end in the number of data points, chrome start and chrome end in terms of the position on the chromosome, and then we also have a column for the mean.
If you know that there's only 1 break at all, why do you test for the 7, 4, 5, 6, 7 breaks at all?
Okay, so okay, so that's a good question. So if we know that there's only 1 break in this particular data set based on the labels, then why do we need to compute this sequence of models at all? It's a really great question. And there's a very interpretable response that you can see in this next figure, actually. So the reason why is because, well, if we only computed this 1 model, right, with the 1 change, which you suggest, well, we wouldn't know if the other models are good or bad. So what do I mean by that? Well, actually it's even easier to explain with the next figure. Right, so remember how we computed the label error in that big matrix of plots? For every one of the labels, we know whether or not it's correct with respect to the changes, right? So the reason why we need to compute the sequence of models is because we need to get some lower and upper bounds for what is a good amount of model complexity for this particular data sequence, right? So we know here, because of the positive label, that this model is no good because it's not predicting a change in this label where it should have a change. And also we know that these models down here are no good because it's starting to predict too many changes in these regions where we know that there's only, here there only should be one change, and here there should be no changes. So by computing the whole sequence of models, it gives us some bounds about what are the appropriate number of changes. So here it's going to be 2 and 4 seems to be an appropriate number of changes. It gives us some weak information about, well, we're going to be using this information to predict the number of changes using these bounds. Right. So another answer to that question, like Rebecca says, is that, well, maybe it's a very long data sequence, and you only have labels in a very small subset of that data sequence. So, in fact, if you only limit yourself to one change because you only have this this labeled one labeled change, then you may miss some of the changes in all of the other unlabeled parts of the data for which you don't have labels. But yeah, it's a very crucial difference with the unsupervised learning framework. You really have to compute a sequence of models instead of computing just one model, because otherwise you don't really get information about what models are good and what models are bad. So that brings me to the next point, which is the model selection function. So the model selection function is a mapping between a real valued penalty and integer valued number of change points or segments. And so to get this model selection function, we provide an R function called penalty learning model selection. And so it takes as an input a data frame with 1 row per change point model and some columns that describe the different models. So you need some ID columns for every separate data sequence. For here it's profile, ID, and chromosome. And then you have 1 column for the model complexity. So this is going to be the squared loss in this normal model. And then there's going to be a column for the, the complexity is the number of change points for segments, and the loss column is the residual sum of the squares, which corresponds to the negative log likelihood of the normal model. And so yeah, what it looks like is a data frame like this, where, like I said, we have 7 models from 1 to 7 segments, and we have corresponding loss values which are decreasing with the number of segments. And so what the penalty is going to do is it's going to tell us for every real valued penalty parameter what is the corresponding model that we would choose using this penalized criterion that Rebecca was explaining in the last part of the talk. So to use this function, we just are going to plug this data frame into the model selection function, and here specifying that the complexity column name is n segments. What we get back is this selection data table where you have 1 row for every model that could be possibly selected for any value of lambda, the penalty. So what it means is between lambda penalty values between 0 and 0.06, what we're going to be doing is we're going to be selecting the model with 7 segments and etc. So one way to visualize this, I'm using a ggplot here with a geom segment. You can think of it when you plot the number of segments as a function of the log penalty. You can see that this is a monotonic decreasing function, a piecewise constant decreasing function. And so for very small penalty values, we're going to be selecting the most complicated model, and then it's going to select successfully less complicated models until eventually for the very largest penalties, we're always going to be selecting the least complicated model with no change points. So why is it important to have this kind of model selection function? Well, The reason why is because we're going to be doing learning in this real valued penalty space instead of doing learning in this integer valued like number of change point space. So actually we're going to this is going to result in a regression problem where we're going to try to predict this real valued log penalty. So how does that work? What we do is, so here in this figure we're only plotting the number of segments, but remember for every one of the models we already know how many incorrect labels there would be. So the next thing we're going to do is we're going to plot the number of incorrect labels along with the number of segments as a function of the penalty parameter.
Sorry.
Yeah.
How do you select the best models for this plot by using the
Yeah, so that's the next figure. The question was, how do you select the best model, right? So it's kind of like, remember the elbow plots from Rebecca's talk, right? It's always going down. How do you know when it's going down enough to be significant? Well, in the supervised learning context, you don't have that problem because instead you can minimize the number of incorrect labels. So we're going to see that in the next figure. So yeah, this is going, so this is the next section. This is computing the outputs of the supervised learning problem. So what the output is, it's an interval of log penalty values that achieves the minimum number of incorrect labels for each one of these data sequences. So remember that we've already computed this object, this zoom error list model errors object. So this came from the label error function. And so it gives us what is the number of incorrect labels, which is an integer valued, it's an integer for every data sequence and every number of segments. And so basically we can just plug that function into the model selection function as star I, which we computed in the last figure, and we can get this EI function, which tells us which of, for every penalty parameter, what is the number of errors that the corresponding model would make. So here, what I'm doing is I'm just, again, adding that as a geom segment in our ggplot. So here, this in the top part of the figure, you see this is the number of segments, like the same figure that we saw in the last plot. And then in the second part of the plot, we have the number of errors. So this is the number of incorrect labels for every log penalty or value. So like we saw, the model with, so over here on the right, with a very large penalty, it's going to select the model with only one segment or no changes. And that's bad because it's having the one error. This is the change that it should be predicting, but it's not. And so at the other extreme, we know that also this is a bad situation with either one or two labels because the penalty is too small, and that's resulting in a model with too many changes. So that results in this interval of log penalty values that results in no incorrect labels. So this is going to be the idea of the supervised learning algorithm. We're going to be trying to find a function, a penalty function that is always predicting a penalty value that's somewhere minimizing this function here, this number of incorrect labels function. Question? This one?
Yes. Is that why it's kept out of the diagram?
So that's a good question. So the question is, why is the model with 3 segments excluded from that diagram? So the reason why is, when we use the segmentor algorithm, it's always going to compute a sequence between 1 and k-max segments. But then when you perform model selection using the linear penalty, it's going to select some it's going to discard some models which will never be selected for any lambda. So for some data sets, basically you see that in this figure when you actually just analyze the mathematics of this penalized model selection function. You see that at some point, well, some lambda values result in the model in 2 segments, and then next, it's going to select the model with 4 segments because actually the model with 3 segments will never be optimal for any penalty value. It's because it's a very, you can see it intuitively in this figure, it's not a very significant change point, right? Here it's just one data point here. So basically, it's kind of automatically excluding some models with very insignificant changes. So yeah, once we have this number of incorrect errors function computed, the next thing is to compute the target interval. So this is this interval here of penalty values that results in the minimum number of incorrect labels. So it's an upper bound and a lower bound that we're going to be computing using this penalty learning target intervals function that we provide. So what you have to do is you have to provide it with your data table that looks like this, one row for every model, and critically with this column errors that tells you for every model how many incorrect labels does it have. And so what you do is you provide this data table to the target intervals function, and you specify the ID variables for every sequence, because typically you're going to be giving it a lot of different data sequences with a lot of different labels. Here there's only one, so it's only resulting in this one row data frame where you see the min log lambda value is about -2.3, and the max log lambda value is about 1.5. But yeah, so typically there's going to be a lot more. We're going to see some more real examples later, but this is just to explain what the target interval computation looks like. So to visualize what this target interval looks like, we're just going to add those 2 points to the last plot using a geom text and a geom point in this ggplot. And so here what it looks like is this black and white point. So again, what it means is we've computed this sequence of models. We know all of the lambda values, the penalty values that would select every one of these models. And furthermore, we know how many incorrect labels there are for every one of these models. So that means we have these bounds now that tell us, well, beyond this black dot, we know that that would result in a penalty value which is too small, that results in false positives, a model with too many changes. And the white dot, it means, well, if you increase any penalty past this, it's going to result in false negatives or models with too few changes. So the main idea of the supervised learning approach to change point analysis is going to be, we're going to be computing this interval of penalty values, equivalently these black lower bounds and these white upper bounds for every one of our labeled data sequences. And then we're going to be using these intervals in a regression problem to try to predict what is the best penalty for a new data sequence. So I think we have an exercise now. Is that right? No, I think, so first, before we get to the exercise, I'm going to show you what it looks like to do this for more data sets. So here in this next code block, what I'm doing is I'm going to do the same computation, but for all of those data sets that we saw in the first figures. So here I'm using a for loop to execute a bunch of code for every one of these separate data sequences. We're going to be executing the segmenter function to compute a sequence of models from 1 to 10 segments. And then for every one of these models, we're going to be saving the change point locations, computing the model selection function, the same steps that we just did. Then, again, we're going to do the same steps again, but for all of these data sequences, we're going to use the label error to compute the number of incorrect labels. We're going to use target intervals to compute the target interval of optimal penalty values. And then here I'm going to use a ggplot to show you what that looks like for all the different data sets.
That's all within data sets. There's no cross-validation involved.
We're going to get to cross-validation later. That's
the second step. Yeah.
That's it.
It's within data set. I just want to be sure.
So yeah, the question is,
Within set regression.
yeah. So the question is, this is all in the training set. Yeah, these are all steps that you do. So yeah, I mean, eventually you're going to have some hidden labels that you've never seen before, and we're going to compute the error with respect to those guys. But that's at the end of the talk. So yeah, I mean, this is just to tell you what it looks like when you do this for a bunch of different data sets. So again, we have these 6 profiles going from rows top to bottom, and then we have these 6 chromosomes which have labels going from left to right. And you see that some of these have these black lower bounds, and some of them have these white upper bounds. And the black line is a plot of the number of incorrect labels, either 1 or 0, as a function of the log penalty. So does anybody know why is it that we have only 1 limit per plot here? In the previous plot, we had 2 limits in a single plot, right? So we had a lower bound and an upper bound. Does anybody know why we only have 1 bound in each one of these plots? Yeah, that's absolutely right. So the answer is that when we go back to the original data set with the labels here, we only have either information that there should be no change points or information that there should be at least 1. So for each data set, we have some weak information, but it doesn't give us both an upper and lower bound.
That's maybe my next question. So why would you not put all this data into the same one? Here it seems you can fit a model to each segment.
Yeah, right. So we're gonna combine all of this, all of these data into a unified regression model in the next step. Yeah. Just trying to explain it step by step. So going back down, we're in the output section, this figure right here. So yeah, so now we have exercise 2 during class. Create a set of labels via visual inspection and visualize how changing the labels would affect the computation of the target interval. So let's look at that on our cloud. So that should be the second code block. I think it's here. So I invite you all to follow along and experiment for yourself. So I think by default we have something that looks like this. And the idea is, okay, well I have some label here where I have no changes, or a normal label, and I have a red label here with 1 change. And then we get a sequence of models that looks like this, where we know that, well, the model with 1 segment is bad, and then going up to here, the model with 5 segments starts to be bad, because I guess we're starting to get a change in this region. So, you know, that's one possible labeling scheme. So we can also try another label scheme for this data set, or we can try a whole nother data set actually. Like for example, here if we have profile number 244 in chromosome 6, we can plot that. Let's try that. So yeah, so here we have a new data set where it looks like maybe there is a change between, say, 110 and 130. So we can change the label and see what that looks like. Is that going? Ready. That's great. Our cloud is working. I'm so happy. So yeah, for this new data set and this new set of labels, what we get is we get something like that looks like this, where the models here from 2 to 6 segments seem to be okay, and then after that you start adding segments, start adding change points where there shouldn't be. So this gives you another idea of how this works, and then you can go down to the next plot and you can see that results in a target interval that looks like this, from about log penalty of negative 3.5 to about 2.5, something like that. So let's go back to the presentation. So the next part, after we've computed this target interval, these white and black dots, that's the outputs of the machine learning problem. That's the y variable, if you want, the thing we want to predict. But so what are the inputs that we're going to use? What are the x variables of the machine learning problem? So to get that, we're going to use this penalty learning feature matrix function. And so what it's going to do is it's going to compute for these profile data that we saw before. We're going to give that to the feature matrix function, and we're going to specify the variables that are the ID numbers for the separate segmentation problems, and then you specify the column name of the data that you want to segment, and then it's going to compute a standard number of features for every one of these problems. So here you get a matrix from with 144 rows and 365 columns, and so the rows are the different segmentation problems, and the columns are the different features. And so the idea is that a priori we don't really know which one of these features is really the appropriate feature to use for predicting what is the right penalty, but we have some machine learning models that will just select whichever ones are relevant, and so we can learn whatever is relevant for whatever data sets as long as you have some labels. But just for comparison, we're going to start out by discussing the simpler big SIC model that we saw earlier. And so this corresponds to this kind of penalized optimization problem that Rebecca was talking about earlier, where you have the loss. This is the square loss for the normal likelihood model. And then you have this penalty term, which here is the number of change points. And here this is the penalty constant, which for the big model, it's always fixed at this constant log d. So this is log of the number of data points. And so what this corresponds to is using a feature xi, which is actually log d. So why is that? It's because, well, when you look at this equation, log lambda, log penalty, so you can write it as an affine function of this feature. So this is this wxi plus b. So what you can do is you can visualize this penalty as actually a linear model with intercept beta equals 0 and slope w equals 1. So what does that look like? We have this in the next figure. So this is the regression plot where we're plotting the output log penalty now on the y-axis, and this feature, which is the log number of the data points, on the x-axis. And the reason why this plot is interesting is because you can really see kind of like the geometric interpretation of the penalty learning problem. So given this certain feature, and given these labels, what we want to do is we want to learn a function that is always predicting below these white lower limits, but above these black, we want to predict below the white upper limits and above the black lower limits. So some function that maybe looks like this, right? So in usual regression, we're trying to just fit a line or a function to a cloud of points, but here it's more like the support vector machine problem for binary classification, where you actually want to find a function that's separating the white and black points. However, it's not exactly the same as a support vector machine, because here the differences are only important with respect to the y-axis. But in the support vector machine, it's the margin is defined with respect to the diagonal. So anyway, so let's visualize what one possible penalty function would look like in this regression context. So this is a visualization of the big penalty function that I told you about, that is always assuming this constant of log n for all of the data sets. The idea is that this solid line here is the regression line, which is going to predict for a given value of a feature what is the corresponding value of the log penalty that we should use. And these vertical line segments are the residuals. So these are the indicating which target intervals are violated, right? So we know that all of these white upper limits are values past which we're starting to get some false negatives, right? So we want to make sure our regression line should be below all of these white ones. So here I'm emphasizing all of the errors, these 5 profiles for which we're predicting a penalty which is too big. So this is a really nice figure because you can really see the benefit of supervised learning very clearly. I mean, you can see that just if you push the regression line down a little bit, you can clearly get a model with fewer errors. And so that's kind of the main idea of the supervised learning approach. If you have these labels, well, you can just do this kind of analysis, and instead of defining some kind of default line, which may or may not be accurate, you can actually define a line in function of these intervals, which is going to be maximally accurate in some sense. So, yeah, just very briefly, we also provide this function, penalty learning target interval residual, which helps you compute these vertical residuals that we're plotting here with a geom segment using ggplot2. And so then in the next plot, what I'm going to do is I'm going to just take these predictions and we're going to visualize them with respect to the real data again. And so like we saw in the beginning of the talk, when we use the big SIC model on these 6 particular profiles, it's resulting in this change point model with 4 incorrect labels. Here we see these 4 purple regions should have change points, but they don't. So question, discuss with your neighbor for a minute. Why are there only 4 false negatives in this plot, but actually we saw in the regression plot there are 5 incorrect target intervals? So it means that here there's 5 sequences where we're predicting a penalty that's too high, but in fact this results in a model with only 4 incorrect labels. Why? How could that be possible? Any ideas? Yeah. Any ideas?
Shouldn't the line have been further down in the image before? Because if you move it down a bit, then the upper left white point would stay above the line, and everything else, all the errors would be smaller. If the discrimination line would be a little lower.
Yeah. So the answer is, well, shouldn't this line be down a little bit lower, and then there would be only 4? But actually, no, I mean, I did the calculation correctly. It's something that really happens.
This is only a guess, but is it you've got lots of points there where you're only plotting a few of the participants in all the line, so you're not plotting one.
The other idea was maybe I'm not plotting all of the data, but I actually am plotting all of the data. So that was it or no? No, for every one of these points, it corresponds to one particular labeled data set, actually. Another idea?
So, is the estimated line has a margin of error at one point falls into some error margin that would not qualify?
Yeah, so the idea is that maybe if it's kind of close, or maybe there's some kind of margin of error that actually doesn't result in a real prediction error or something like this. And so that's pretty, it's a pretty decent response. And so actually, the full response is explained by this figure here, which shows you, again, it's the plot of the number of incorrectly predicted labels as a function of the predicted log penalty values. And so here what I've added is I've added this blue dot, which is the predicted log penalty for each one of the data sequences. So you see that most of them are predicting on the 0 part of the incorrectly predicted labels, but you see, for example, this one, the predicted value is above the white upper limit, so here it's making an error. But you see for one of these, it's actually above the white upper limit, but it's actually in a region where you have actually the error function is going up, and then it's going back down again, and then it's going up again. So this is a phenomenon that can happen when you look at this 0-1 style loss function. There could be more than one minimum, and so actually how we define the target interval, it's the biggest range of penalty values. So it's possible that there is another model that achieves 0 errors, and so basically this is kind of a limitation of the method. We're kind of assuming that this bigger one is the region that's of interest. It's kind of, in this case, it's the simpler model, I think. So we have a few exercises that you might want to think about doing after class that I'm just going to briefly discuss. And so the idea is that, you know, here we just use one feature which corresponds to using the big penalty, but you can think of any other features that might be useful for predicting log penalty values. And you could do the same plot, and maybe it might be resulting in even better prediction, right? Or I mean, you might be able to think of some kind of line that could result in better prediction in a different feature space, right? Depending on the arrangement of the points, you could have full separation, and you could be able to easily find a line that separates the two. In this particular feature space, for this particular data set, actually there's no linear regression line that will fully separate the white and the black points. But by calculating another feature, you may have a different arrangement of points and they may be more well separated, so you could find a regression line that would work better. And another exercise is trying the different penalty values. So the one that we saw in this last regression plot is a particular value of the penalty, but you can try different ones, and you can try to plot the regression line that would correspond to the different penalty values. But yeah, I'm not going to do these exercises right now, but if you want to see if you understand this fully, you can go back and you do these exercises after class. Now I'm going to get to the really interesting part, the supervised learning. So now we've calculated the inputs and outputs of the machine learning problem. So now we're going to be able to apply these supervised machine learning algorithms in order to learn this penalty function with a better change point prediction accuracy. So the first method I'm going to discuss is called servreg, and this is a part of it's a recommended package, so it's a part of the survival package. And so what it's implementing is an unregularized interval regression model. And so I'm not going to go into details of the mathematics, but basically what it's doing is, well, before we had this penalty, which is just log D, kind of a constant for all data sequences. But so what we're doing is we're just kind of relaxing this assumption. So instead of having a penalty which is always log D with these constants in front of it, 0 and 1, so what we're going to do is we're going to assume that these constants can be learned. So rather than assuming a constant beta here of 0 and a constant w of 1, we're going to be able to learn the slope and the intercept of that regression line using this servreg method. So yeah, to load this learning algorithm, you use the library survival. And then, so to set up a simple cross-validation experiment, I propose to hold out chromosome 11 as a test set. So here I'm constructing a train DT, this is a train data table with all of the data sets, with all of the labeled data sequences that are not on chromosome 11. And then we're going to do a regression on all of the other data sets. And so servreg is a function like LM or like other R modeling functions where you can give it a formula where on the left side it's the output and the right side they're inputs. And so on the left side you have to have one of these serve objects which is going to specify an interval of output values. So usually in linear regression you would specify like one of the variables as the output regression variable. But here what you have to do is you specify the interval of output values. So the first argument of the serve function is the lower limit of the target interval, and then the second argument is the upper limit of the target interval. And then here, tilde feature, it means we're going to use that one feature for doing the regression. And here you can specify what kind of distributional assumption Here I'm using the Gaussian distribution, but there's other choices that you can maybe do for exercises. So here already, when we look at the output of the servreg function, you can already see that there's a difference from the standard unsupervised penalty. And so by looking at the coefficients, where here we see the intercept is negative 4.7, which is clearly different from 0, which was the intercept of the BIC model. And the slope here is 0.7, which is clearly different from slope of 1, which was the slope of the BIC model. And so to visualize that in the regression space, we make the next plot. So here I'm using geom AB line and geom segment again to visualize the model. And so here we're visualizing using this this orange line for the servreg model, and with these orange vertical line segments for the residuals. So you can clearly see that, I mean, basically what the servreg model is doing is it's just like we described we should be doing intuitively. You just basically push the regression line down and you change its slope a little bit until you find a regression line which is minimizing the number of incorrect intervals. So that's the basic idea of the supervised learning problem that we have to solve. So another way to visualize those those predictions is in this next code block. We're going to be doing the same kind of analysis, computing what would be the corresponding penalty. The corresponding penalty values in this this plot of the number of incorrectly predicted labels versus the predicted log penalty or log lambda values. And so here, what I've done is I put an orange dot for the predicted log penalty values. And so you can see, for example, in this data set, the BIC model was predicting, here the BIC model was predicting 1 error, and so by using the supervised learning method, now it's down to 0 errors for this particular data set. And so again, this is the training data, so this is how the model is training. And so this, and this quadratic orange line here, this is just to kind of give you some kind of geometric intuition about what is the loss function that the algorithm is trying to minimize. So for those of you who study optimization, you probably know that you can't directly minimize a non-convex function like this 0-1 style loss in black. So in fact, what the servreg model is doing is it's doing some kind of convex approximation, and that's this orange function. And the reason why it works is because it has these quadratic tails which increase as they go past the limits. So basically, the algorithm is going to find some region, try to put all of these orange dots in a region of the space where these quadratic functions are very small. That's just to give you some intuition about what the algorithm is doing. And then to visualize what the predictions look on the training set, again, these are all, well, so again, we set aside the chromosome 11 as a test set, so we can use that to kind of evaluate at least qualitatively. But you can see already that it's doing a lot better. Like before, in the last plot with the unsupervised change point model, we saw that there were like 3 false negatives over here. Now we're left with only 1 false negative. So already we can see that we're doing a little bit better. And so I think we have a third exercise. So I think in the interest of time, I'm just going to skip this exercise. So, because it seems like it's the end of the day and we probably just want to get this over with, you know. But yeah, so next thing I'm going to discuss is the interval regression CV model. So this is kind of like the real machine learning approach, right? So the last model that we talked about, I mean, really it's only doing this simple linear model, learning 2 parameters, the slope and the intercept, in this very simple 1 feature model. But I mean, the real interest of machine learning for change point detection is that we can have these more complicated multivariate models where you can just use L-run regularization to select what features are relevant, right? So in practice, in real data, nobody knows what is like the real penalty that people should choose. You know, like Rebecca says, it's an open research question. So the really advantage of using machine learning is it's just practically it's an easy way to get a penalty that works for your labels. So you're going to throw it as many features as you want, and it's going to just select whichever ones are relevant for predicting the right number of change points, basically. So it's kind of like a black box. You don't know exactly why it's doing this. I mean, there's a linear model, of course, but you know that it's going to be giving you very accurate results. So again, going back to this equation, we have this lambda value, and so again, we're just relaxing it. Before we had a simple function of just one variable. Now we have a multivariate function with this vector of features x, and then we have this vector of learned coefficients w that we're going to be learning along with the intercept beta. And so what does that look like in terms of our code? Typically, so what we're going to be doing is we're going to be computing some kind of feature matrix that looks like this. So for the small data set we looked at before, there's 30 rows and 256 features. And so we're going to be giving this matrix as inputs in the machine learning problem to this interval regression CV function. So this interval regression CV function is defined in the penalty learning package. And like I said, the two main inputs are the numeric input feature matrix, one row for every observation or data sequence to segment, and one column for every feature. And then the second argument is a numeric output target interval matrix. It's the number of observations or data sequences with labels, and by the number by 2. So that's the lower and the upper limit of these target intervals. And so, yeah, so you're going to basically, what we do is we give this to the interval regression CV function, and it's going to give us this fit.cv object here. And so what it's, when we look at the coefficients, you see that it's, it's learning. These are only showing the non-zero coefficients of the model. So it's about 15 or 20 features. So what happened is, we gave 256 features to this model, and for some reason or another, it selects these 15 or 20 as the ones which are important, along with these coefficients.
Just talk a little about what the features are. I mean, is it based on the data you have, or is it based on some knowledge you have about
Yeah. The question is, where do the features come from? And so basically, it's just a bunch of simple statistics of every one of the data sets. You compute the mean, the standard deviation, the quantiles, some other variance estimates, number of data points, all this stuff. You just throw it into a big feature vector, and the machine learning will just pick whichever is relevant. Actually, a linear combination of whatever is relevant.
So basically, you're saying, let's say that one of your small was slightly higher than the other. Does that have an impact on your algorithm? Is kind of that what you're saying?
So yeah, we have another question that is in the regression plot, right?
No, not that one.
No?
The big one with all the
In this plot?
So basically, you're saying, could it affect the mean in each of these small buckets? Could that affect the lambda?
I don't really understand, but maybe we can talk offline. Sorry. Just want to get through this. Anyway, so when you look at the results, when you fit this interval regression CV function, you get a little bit better prediction accuracy. Like in particular, now we actually have a model where all of the labels are satisfied. In particular, even in this chromosome 11 data set where we were having a false negative before. So that's a little bit of an improvement with respect to the single variable model. So yeah, just very briefly, these are only two methods for doing this like interval regression penalty learning, and there's some other packages here that you might want to try if you're really concerned about accuracy. So the last thing I want to talk about before I let you guys to go is about evaluation. So this is another really cool thing that we can do using machine learning, using these supervised change point analysis. So usually with a typical unsupervised change point analysis, you don't really have any way to quantitate like what is the change point detection accuracy or error rate. But using these labels, it's really great. All you have to do is you just use this label error function, you compute what is the percent of labels that you guessed correctly, right? So you just hold out a test set like we did with chromosome 11 earlier, and then you just predict what the prediction, compute what the predictions would be on that test set, and then you just compute how many labels did you get right or not. So it's just kind of like a quantitative, more systematic way of evaluating these change point detection models. And so in particular, we have a function called penalty learning rock change, which is going to be able to compute receiver operating characteristic curves, which you may be familiar with from binary classification analysis. So what this is going to do is going to evaluate what are the error rates for all possible thresholds or values of this intercept parameter. And so yeah, basically to use this function, you just have to give it this model errors database of what is the number of errors for all possible penalty values and all possible problems. And then you give it what are the data sets in the test set here with chromosome 11, again for this small trained test split. And then it's going to be giving you back the rock curves and the AUC values, the area under the rock curve. And so what it looks like for this small trained test split that we looked at before is it looks like this, where you have the AUC values here. Here it's 1 for the interval regression CV model, which is pretty good. And then you have a little bit lower for the other two models. And again, you have the error percent, number of incorrect labels as the errors here. And so you can visualize the rock curves like this. But clearly, since there's so few labels in the small data set that we're looking at, the rock curves are very jagged, and you don't really know what is if there's a significant difference. So now here's when we're going to go to the full data set. So in the whole neuroblastoma data set, we have 3,418 labeled data sequences. So we're going to do a test split on all of those data and then compute the test error rates with respect to a, I think, 5-fold cross-validation experiment. And so yeah, I've pre-computed all of the models here because I mean basically to run all of these segmentation models like for 3,000 sequences will take very long to do interactively. So if you do these computations yourself, I suggest just downloading these pre-computed models that I have, or you can pre-compute it again using this script that I provide. But again, so basically what we just do is we just do the same sequence of steps that we did for these smaller subsets of the data. And here what I'm going to be doing is I'm going to be learning a multivariate penalty function using these features here. Again, for time considerations, I wanted to do the training on a small subset of the features, but if you have more time, you can do it on all of the features. It should be no problem. And then, yeah, so for the cross-validation code, I mean, basically what I do here is I say, okay, we want to do 5-fold cross-validation, so I define the number of folds here. Then for every one of the data sequences, I assign it to one of the 5 test folds. Here I'm using the sample function to randomly choose one of the 5 folds. And then I'm implementing the cross-validation experiment in the for loop here over the test fold variable. And so for every one of these trained test splits, what I'm going to be doing is I'm going to be computing one of these interval regression CV models, and then we're going to be computing also for comparison the SERVREG model and also the BIC model. We save all 3 of these models in a list, and then we compute what are the test errors with using this penalty learning rock change function. So for every model and for every trained test split, we're going to have a quantitative measure of how accurate that model is. So when you plot the rock curves that we get, it looks something like this. And so you can see they're a lot more quantitative, and you can see more of a significant difference between the different methods. And in particular, you can see that, well, so here I'm plotting one rock curve for every one of the 5 test folds. So you can see that here the big SIC models tend to be a little bit lower than an interval regression CV and the SERVREG models. And in particular, I'm plotting the predicted penalty threshold using these points here, and you can see that the big SIC model predicted values here tend to be a bit lower down than the interval regression CV and the SERVREG models. And so what that indicates is it has lower true positive rates or higher false negative rates, meaning that it's actually missing a lot of change points that it should be detecting. And so another way to look at those results is by just computing what are the % incorrect labels and the AUC, the area under the rock curve. And so in this figure, I plot a dot for each one of the numbers in that 5-fold cross-validation experiment. So you can see very clearly that the big sick model here is quite a bit less accurate than the SERVREG and the interval regression CV models. In terms of AUC, you're getting quite a bit better when you go to the SERVREG model, and then a little bit better by using the multivariate interval regression CV model. And so more generally, I mean, these are results that you can, these particular numbers are specific to the neuroblastoma data set, so like 92% for the BIC and 98% for the supervised learning. But I mean, in general, you can expect a big improvement when you go from unsupervised learning methods like this to supervised learning methods where you're actually using the labels to learn a penalty function to predict the number of change points that you want. So the second thing that I wanted to emphasize is that this is a 5-fold cross-validation experiment, but in fact, if you're going to do this on in a real data context where you really want to learn the most accurate model for all of these unlabeled data sequences, you should probably just train on all of the training data that you have and use that to predict on all of the data that you have. And so I have a figure that shows what that looks like here. I don't know if that's going to load, but anyway, so that's basically it. So yeah, I hope I was able to convince you of the benefits of the supervised learning paradigm in change point detection. So basically, when we have labeled data sequences with a common signal noise pattern in the different data sets, we have some supervised learning algorithms now that can be used to learn a penalty function that is able to predict change points which are much more accurate than unsupervised methods. And the second main benefit of the supervised learning approach is that we can actually use these labels to quantitatively evaluate the accuracy of the different change point detection methods. So yeah, I guess it's not loading, so I can't show you the final example, but thanks very much for your attention, and I would be very happy to have your questions, and yeah, have a nice conference.